Hey everybody, welcome to today's video. So in chemistry we study matter and the changes that it undergoes, whether those changes are physical changes or chemical changes and reactions. But either way, no matter what change matter is undergoing, there is always an accompanying energy change. And the study of those energy changes is known as the field of thermochemistry. So let's define a couple of terms for this study of energy change. We have the term system, which refers to the actual molecules that are doing something, or the atoms or the ions. And then the surroundings are literally everything else. So let's suppose that you have a system. Maybe it's a dissolving process and it is happening in aqueous solution. The system would be the molecules that are dissolving, and the surroundings would be the water that is holding them together, and the beaker that's holding the water, and your hand that's holding the beaker. It is literally everything else except for those particles. All right, so let's look now at a graphic. Let's talk about some type of change that's happening. Let's just say it's happening in an aqueous environment. And so we have some particles that are doing the change, and then the surroundings, and let's suppose that surroundings in this case is some water. All right, so at the beginning, you're going to put your thermometer into the container and record or observe that starting temperature. Now, here's the first thing I want to point out. When you put your thermometer into where the change is happening, that thermometer is going to be measuring what the surroundings are doing. Your thermometer or your temperature probe cannot possibly be inserted so that it is only touching the system molecules. That just can't happen. So in goes the thermometer into the whole thing, and it's going to be recording what the surroundings are doing. Let's suppose that as the change occurs, you observe that the temperature goes up. So we define or we describe that type of energy change as exothermic. Now, exothermic means that heat energy is exiting the system. So we have energy leaving the system and going into the surroundings. And therefore the surroundings feel hot, and we observe that with the rise in temperature. Now the surroundings is feeling hot, but it's the system that is experiencing a negative change in heat energy. Okay, think about that for a minute. Heat energy is leaving the system to go to the surroundings. The system is experiencing a negative change in its heat energy, and the surroundings feel hot. Okay, let's compare that to a second change. And again, we put our temperature probe or thermometer in there, and we acknowledge that it is going to be observing what the surroundings are doing. And as the change occurs, we're going to observe this time that the temperature goes down. The surroundings are getting cold. You might even feel that with your hand. When your hand holds the beaker, you might be able to detect that the surroundings are getting colder. That type of change is described with the term endothermic. Endothermic means that heat energy is entering the system. And how can it be entering the system? Well, it's coming from the surroundings. And the surroundings, therefore, are going to feel cold. And the system is experiencing a positive change in its heat energy. Heat energy is entering the system, positive change, and the surroundings feel cold. Let me just bring up a physics and chemistry principle here. This is actually the first law of thermodynamics, which tells us that energy cannot be created or destroyed. Side note, in a nuclear process, it can be. But in our study of chemistry, we're talking about physical changes and chemical changes, not nuclear. Okay, so we have this guiding law. Energy cannot be created or destroyed. It can, however, be transferred. So this is going to be important to us as we continue this thermochemistry. In each of these cases, the energy is leaving either the system, going to the surroundings, or leaving the surroundings, going to the system. Okay, I hope my color coding is helpful to you. Things to remember: exo is experienced as surroundings feel hot. An exothermic change is always denoted with a negative value. Endothermic, where heat enters the system, is experienced as feeling cold. And that value, that value is going to be a positive number. All right, now let's take a look at what's happening on a particle level. Here is my beaker of water. Okay, and let's suppose we've got water molecules in here. And as we've said before in an earlier video, there are forces of attraction that hold those molecules together. They're called intermolecular forces, or IMFs. And we're going to put in some solid solute, potassium hydroxide. In this case, it's an ionic solid. So there are Coulombic attractions between the cations and the anions that hold this solute very firmly in place. It's a solid, so there's very little motion, maybe a little vibrating, but Coulombic attraction really holding them together, and IMFs holding these liquid molecules so that they're touching each other, but they are, remember, kind of free to roll around. Okay, in this dissolving of potassium hydroxide by water, there's really three energy pieces going on. So let's first of all talk about the endothermic steps. Okay, so one of the first things that has to happen for dissolving to happen is these water molecules have to pull away from each other a little bit. They have to do that to make room for the dissolving solute. All right, see my guys in a tug of war? Whenever you're trying to overcome forces of attraction and pull the particles away from each other, that requires energy going in. So this process right here actually has a number value, and it's a positive number. Okay, there is another force of attraction that has to be overcome. That's over here between the cations and anions. And that Coulombic attraction has to be overcome so that the cations and anions can each go into solution. That also is going to require that energy goes in. And that separating, that endothermic step also has a magnitude. It has a number value, and it will also be positive. Okay, now let's consider the coming together of this little water dipole and the cation. Snap. They attract to each other. Or here comes another water and the anion, snap. Okay, they are drawn to each other. So whenever particles attract each other, energy is released. So I want you to think like of these two magnets. Imagine bringing two magnets close to each other and they snap together. Just maybe that snapping sound will help you remember energy is released. So that particular attraction that is being allowed to happen is an ion dipole attraction. And that snapping together involves an energy change, and it's exothermic, so its number value is negative. Now, in this dissolving process that I've just shown you, there were two pieces that had positive values, and then a piece over here that had a negative value. When you add those three pieces together, the net is either going to be positive or negative. And it turns out that in the dissolving of potassium hydroxide by water, the net effect is overall exo. So this number that is negative must be pretty big compared to these two smaller numbers that were positive. That's an exothermic dissolving process. Let's look at one more and put my waters together. Take the potassium hydroxide away. And now let's look at the ionic compound ammonium chloride. Okay. Held together, cations and anions, by a strong Coulombic attraction that has to be overcome. So that's going to be an endothermic step that has a positive value. There's a number associated with that, and it's positive. Meanwhile, we've got my water over here, held together tightly with IMFs, intermolecular forces, and those waters are going to have to pull apart from each other. That will be another positive number. And then we're going to let the ions and the dipoles attract each other, and that process will release energy. Whenever particles attract to each other, energy is released. It's an exothermic process. It has a number value that is negative. So here comes water, and it's attracted to the cation, snap, exothermic step. And here comes another water, attracted to the anion, snap, and they come together. I want you to notice that when ammonium chloride dissolves, this polyatomic cation is not coming apart. It stays intact as NH4, the polyatomic ion. It is simply being pulled away from the anion. All right, so in this dissolving process, again, we had two endothermic steps, each with a positive value, and we had one exothermic step with a negative value. But we find that this overall dissolving process is net endothermic. So the magnitude of the two endothermic steps that are positive must be greater than the one exothermic step that's negative. All right, guys, so that's a lot of conceptualizing for thermochemistry. We will be doing a lot of practice with this, but I hope that that is a good start and was helpful. Thanks.